All right, thanks very much everybody. The purpose of the talk today is really just to present a recent paper that we've published, taking advantage of a fairly unique and large data set that I've put together with a couple of key collaborators, especially Sean Wilson and Nick Graham. And basically what we've done is we've compiled all data that's available on changes in the abundance of reef fish following major disturbance events, so that we can look at the differential susceptibility to things like coral bleaching and coral loss. But in terms of the overall purpose of today, I promised Jenny Lacken that I wouldn't actually talk about climate change. That's why I'm talking today and not yesterday. So I'm just going to focus on the latter part of the study, where we use this same data to try and look at the importance of biodiversity, in a sense, in terms of preserving ecosystem function. And this is a key sort of concept that underlies resilience theory, which no one, especially in the coral reef literature, has really tried to tackle. So the idea is that we know there's lots of species. A recent paper by Camilla Mora put the number of species for animals around the world at about 7.7 million. This is based on a somewhat unusual relationship that emerged when you look at the higher taxonomic orders, and then if you just continue that trend, you can see that, you know, in terms of the disparity between here, this is the described species and this is what you predict based on this relationship. So they've used this to try and firmly establish what they think is a starting point for how many species there are. And we can look at this in a number of different ways. If we focus on marine biodiversity, this is the total biodiversity, not just animals, across all taxa. In terms of the marine biodiversity, they estimate that there's just over about 2 million species. If we take the value that's bandied around at the moment, the 25% of all marine biodiversity is on coral reefs, we come up with an idea that there's about 500,000 coral reef species. But that's all well and good, but just knowing that there's lots of species doesn't really tell us anything. And the one thing that's definitely emerged, both from Sally's talk and also in Andrew's talk, is that this biodiversity isn't equally distributed around the planet. And so what is the real benefit of having lots of species? And a lot of people before me have been thinking about this, and so a lot of the seminal work by people like Dave Bellwood have talked about the functional redundancy. And so one of the ideas that's emerging is that if you have lots of species, it might be beneficial in the sense that you've got this functional redundancy and you can afford to lose some species, and at the same time it won't have any net effect on ecosystem function. So this is the sort of predicted relationship. This is what everyone's talking about as probably the most important function on coral reefs. We have a whole bunch of different species which potentially are herbivores. And so we think of these species as being critically important in preventing reefs from going from here to here, the sort of dreaded phase shift. And if we think about this relationship, it's sort of suggested that there's there's a saturating relationship here, where above a certain level of species you don't get any added function. So if you're up here, you can afford to lose a lot of species before you actually start to erode this function. That's the theory at least. And there's a little bit of data that's emerging which is now suggesting, well, this isn't the full story, okay? And the first thing I'd say is herbivory a single function? Is it really important to look at this as just one function, or are there a number of distinct functions which underlie this whole phase shift? And that's really where Dave Bellwood's making significant inroads. Okay. The other important thing that emerges is even when you go to a given place and say, well, are all these species equally important? Just based on the patterns of abundance, we can see, if we look at herbivorous fish at Orpheus Island, we can see that there's marked variation in abundance. And this is the same for a whole bunch of different functional groups. You tend to have one species which is really driving the function, which really has a disproportionate role. And so if you lose that species, you're probably in trouble. The theory is, however, that a lot of these other species, which are at the moment not so abundant, may actually have some compensatory increase in abundance and therefore preserve the function even if you lose that most important species. And there's actually ways to test this with some of the data sets that are around. And so I immediately looked at the caging study that we did a while back. And the idea with this caging study was look to to try and understand the ecosystem effect of removing the larger herbivores. So before everyone says, well, these guys aren't herbivores, at the time we were sort of thinking about this, we were arguing, well, we're just going to take out the large herbivores. There's no way we can effectively exclude these. Let's actually just see what happens. And in a way, it's a really neat study to see, in the first instance, where there's any compensatory change in the abundance of these species if you take these ones out of the equation. So we've got that data, and we had a look at it. There's two main blenny species at Orpheus Island. And these are the sort of treatments. The blue and the green are just our cage control. So inside those plots there's a lot of other herbivorous fish, not just the blennies. Inside the full cages there's virtually no other herbivorous fish. And there is an evidence, at least in the first year of the study, that the abundance of these blennies was much higher inside the full cages than outside the cages. But in terms of this sort of notional ecosystem function of herbivory, they did bugger all. We've still got the situation inside the cages where there was lots and lots of macroalgae. So there was a compensatory increase in the abundance of these guys, but it wasn't that they were, necessarily benefiting from having less other competitors and things like that. There's probably just simply a lot more food here for them, even if those other fish were around. The fact that there's a huge increase in the three-dimensionality of their habitat probably provides a huge access to additional resources. But the other thing about this notion of functional redundancy is this concept of response diversity. So functional redundancy is going to be meaningless if you don't have the response diversity. And the idea of the response diversity is that if you have a given impact or a disturbance, some fish will increase in abundance and others will decrease in abundance, and so that you won't actually get a net change in the overall function. Well, this seems, just completely non-intuitive, in the sense that if all species within a given functional group are ecologically equivalent, they're probably going to share a lot of resource requirements, and if those resources are depleted, then you can imagine the entire group is going to be affected. Okay? And I find it really hard to think that, for example, in this group, in terms of the coral feeding butterfly fish, if you have a disturbance that causes coral loss, so this is data from the Central Great Barrier Reef following a bleaching event in 2001, all the coral feeding butterfly fish on that reef declined in abundance. Now, admittedly, they actually had different trajectories, so this species here, Chaetodon lumulatus, actually hung in there for quite a while before it really showed a dramatic decline in abundance. But after about 5 years, all of these things have really essentially lost their ecosystem role, the functional role that they're providing, so there's essentially no corallivory on these reefs. And I should say that on these reefs, it's not that there's no coral. There's still about 30% coral, but it comes back to what Dave Bellwood was saying, there's no acropora or poslopora. So this was a fairly selective disturbance, but it really had a dramatic effect on the key resource for this entire functional group. So there was no response diversity in this group. But you could argue that this is a fairly specialised group. Let's look at the larger data set. And so we took all the data we have and we tried to come up with a sensible sort of approach to defining the functional groups. Now, this is probably one of the most controversial issues at the moment. What are the sort of appropriate functional groups? And everyone uses slightly different functional groups. So what we decided to do was take a sort of hierarchical approach. And in the first instance, we just came up with 4 primary functional groups: corallivores, herbivores, omnivores and carnivores. And then we divided those into some of the secondary functional groups that are most commonly used in the literature at the moment. And Andrew Hoey went through and ascribed all the different species to both a primary and a secondary functional group. Now, we did do some merging in terms of the logistics of the data set, where we, in order to test some of these things at the higher level, we wanted a lot of species in the data set at each of those different levels, so we actually pooled some of the groups. And we justify why we do that, why we clump the omnivores and the planktivores, and in the end we ended up calling them mostly planktivores. So this is the sort of data set we went on, and we wanted to really understand whether there's response diversity among all these species. So this is essentially the way the data comes out. So along this axis, you've got the change in the abundance of species relative to the change in the abundance of coral. So these are all studies which have documented at least a 10% coral loss over a really short period of time. So it's associated with an acute disturbance, be it coral bleaching, outbreaks of crown of thorns. What we do is we look at the change in the abundance of this particular species relative to the change in coral cover. So this threefold change in abundance means for a 10% decline in coral cover, there was a 30% decline or more in the abundance of the fish. 0 means no change, okay, and if they actually increase in abundance, you've got the green section here where, in some cases we've got situations where herbivorous fish increase sort of tenfold following a relatively minor change in coral cover. So you've got a wide spread of responses. And this is just the frequency distribution of species responses. So we just work out the proportion of species within this certain group which are in each one of these categories. This shape of this curve is your response diversity. And so there's a number of different ways of actually capturing this. You can look at the overall range, but you can see they all have a complete range across all possibilities. The other way to do it is actually look at the shape under that curve, or importantly, the range, the extent to which they're concentrated around the modal response, which is essentially kurtosis. So that's the key thing we use to assess the differential responses among these different functional groups. But in overall, the interesting story is that out of the 754 species that we've got data for, 60% of them decline in abundance. And so whether you're looking at carnivores, herbivores, planktivores or corallivores, the mean response for all those groups is generally negative. So while you do have some species increasing in abundance, the overall story is that it's generally bad for all these functional groups. Now, this is interesting because up until fairly recently we thought that there were only about 10 to 12% of species that we could really suggest were obligately dependent on live corals for either food or for shelter. So things like these coral feeding specialists and the things that Dave Bell was alluding to that live inside the corals. And yet about 60 to 70% of all species experience a decline in abundance when you have a fairly moderate decline in coral cover. So that's a really important change in our thinking here. Now, in terms of actually looking at the role of these functional groups and whether they're really important, if you expect a high level of response diversity, you would expect that the variation in the overall data set would be driven by species. So this is a plot of the variance components saying whether the variance was explained mostly by our primary functional groups, our secondary functional groups, by species within these groups, or the error. So this is where we've got multiple records for different species. And if you have high response diversity, we'd expect the relationship to look something like that. Primary functional group, because of a lot of discussion about them not actually being that sensible to use, would have a relatively low contribution, and it's all at the species level. In fact, we found the complete opposite. Although there's a lot of discussion about these broad classifications, that's where all the variation really is explained. And that explains significant variation compared to these secondary functional groups. And to look at that, I can show it this way. So you can see just across our 4 major functional groups, you can see that there is strong differences, where the corallivores have almost no response diversity, the carnivores have relatively much more response diversity. Now, we can't look at all the secondary functional groups within these primary groups simply because of the distribution of the data we have across those secondary functional groups. We've only got sufficient data for certain ones. But you can see there is variation within some of these. Okay, so among the herbivores, the farmers, the territorial farming damselfish, tend to exhibit relatively low response diversity compared to things like the croppers. So there is a story within these functional groups, but these sort of 4 main functional groups tell the story. Overall, I'd suggest that the response diversity was much lower than we really expected. The other thing we did when looking at this is then say, well, what is the effect on overall species diversity? And so on this axis we've got the change in species richness, the proportional change in species richness relative to coral loss. So in the first instance, the first thing that emerges is as you have increasing coral loss, you tend to get an increasingly negative effect on species diversity. There's a lot of noise in here, obviously, and part of that variation is explained by the different types of disturbance. So on one hand, we've got disturbances like coral bleaching, which just cause coral loss and no fundamental change in the physical structure of the habitat. On the other hand, we've got things like cyclones, which not only kill corals, but they also destroy the physical substrate. They lead to lower structural complexity. And you can see that if you have a reduction in structural complexity on top of the coral loss, that then generally has a more negative effect. The important thing about this data is we're not documenting extinctions of species. This is just a change in the relative number of species, usually just counted on a transect. Okay? So in this particular case, we do have really extreme examples, okay, where a 60% decline in species richness probably does correspond with some local extinctions. But the local extinctions we're seeing are really among these highly specialised corallivores and not among any other groups at the moment. So Oxymonycanthus, the coral-feeding filefish, has gone locally extinct in southern Japan, and there's various reefs around the place where this highly specialised butterfly fish, Chaetodon trifascialis, has gone locally extinct. So the take-home message from this, I guess, is that coral loss is generally bad, and the story is even worse if we get declines in structural complexity. And so in this particular case, when you go from here to here, this is the situation in southern Japan following outbreaks of crown of thorns. You can see up to a 65% decline in the diversity of reef fish. So coming back to our original question, is biodiversity important? The way we wanted to look at this is look at the differential responses in different parts of the world. And this is data that a large group of us have been working on with Camilla Mora, and essentially this relationship here was at a sort of initial attempt to see whether there's a relationship between biodiversity and ecosystem function. So we expected to see that relationship I showed you early on, where you start to get an asymptotic relationship. We've got diversity along here. If you've got lots and lots of diversity, you expect to start to see that asymptote emerge. Now, we only use biomass because there's no clear way to measure ecosystem function across all species. Okay, so this is a sort of a surrogate for that. But we can see that there's a clearly non-saturating relationship. So in all cases, whether you're in a high diversity area like the Indo-Pacific archipelago, there's a straight line relationship, and there's no evidence that it's asymptotic. So this says that all species are important. It also says that the loss of any species potentially will undermine your functional response, your functional resilience. So in terms of how we think about that, we've tended to think, well, high diversity systems may actually be more resilient or less susceptible to these changes, because if you've got this high functional redundancy, you can afford to lose some species. Well, we need to change that thinking, because not only is there no apparent relationship here where you have this saturating relationship, all species are important. The other thing is that when you look at the degree of species loss, so we look at the standardised response because this is relative to the degree of coral loss, some of the high diversity systems are the worst affected. So when you have a given disturbance in a high diversity system, you lose far more species than if you are in a low diversity system. So it's not that you're losing a relatively small proportion of your species and therefore there's other species that can take over the role. The disturbances are having a disproportionate effect on species loss within those areas. The interesting thing here is in the Caribbean, despite a lot of data studies where we've had a mean of 50% coral loss, the overall standard response in terms of the fish is actually positive. And that's probably reflective of the sort of story we've had about shifting baselines, that a lot of the highly susceptible species have long time ago disappeared from that system. So in conclusion, a very large number of coral reef fish, approximately at least 60%, are negatively affected by declines in the abundance of live corals. And this is sort of reiterates the story we've presented previously, but this is an ever-expanding data set. Also, in terms of the specific question about response diversity, and this is very much the first step in trying to come to terms with the way we measure response diversity, we argue that it's generally very limited, especially within the groups with very strong reliance on live corals. And now that's expected. The key question is how do you actually really measure the severity of disturbance for something like a herbivorous fish? coral loss probably isn't the relevant measure of disturbance. If we actually work out what the appropriate measure of disturbance is, we'll probably see that there's even less response diversity in things like herbivorous fish than what we've currently captured. And the final thing is that from this sort of initial study, the story is that probably all species make an independent contribution to ecosystem function. So that even in high diversity ecosystems, there'll be a loss of function with declines in biodiversity. Thanks very much.